Hi, welcome to the BCD numbers video for the Intel 8085 and Zilog Z80. BCD stands for binary coded decimal. If you're interested in the origin of BCD numbers and the usage of it, I can recommend the following two videos of the channel Computer File. Today, new CPUs, when they are used in 64-bit mode, have no BCD instructions implemented. BCD calculations are mostly done with the help of software libraries. A lot of calculators, like the Sharp or HP series, had an extensive implementation of BCD arithmetic instructions. BCD is still used for displaying decimal numbers in clocks, counters, calculators, or even in financial or in science to bypass fractional rounding errors. In BCD, a digit is represented by 4 bits. 10 digits represent decimal numbers from 0 to 9, which have the same representation in hexadecimal. The 8421 BCD corresponds with the binary format. Numbers from 10 to 15 are not used. Four is represented by 0010, and 1 is represented by 1000. So you need 1 byte for 2 decimal digits. Another example, 93. 3 is represented by 1 and 2 is 3, and 9 is 1 and 8 equals 9. Let's jump to the simulator. The Z80 part begins at 11 minutes 22 seconds. Before I show the first BCD example, I want to return to the flag register, which we have already covered in earlier video, with the exception of the AC flag. The AC flag stands for auxiliary carry, and it acts a little bit like the carry flag here. If by an add instruction a carry occurs between the 7th and the 8th bit, the carry flag will be set, and if by a subtraction a borrow occurs from the 8th to the 7th bit, the carry flag is also set. It's quite similar with the auxiliary carry, but only for the lower 4 bits, which means if by an add instruction there is a carry from the 3rd to the 4th bit, carry flag is set, and by a subtraction, if a borrow occurs from the 4th to the 3rd bit, the carry flag is also set. Or in other words, if by an add instruction the number does not fit in the 4 lower bits, the carry occurs, the carry flag is set, otherwise it is reset. Or by a subtraction, if the number fits again in 4 bits, the auxiliary carry flag is also set. I will show you it in an example, it's easier to understand. Loading the accumulator with 14, incrementing the accumulator, incrementing accumulator, incrementing accumulator, decrementing accumulator, decrementing, and last decrement. So, accumulator is loaded, incrementing it. Number does still fit in 4 bits, 15 is the last number, so auxiliary carry flag is cleared. Incrementing it, the number 16 does not fit in 4 bits, so auxiliary carry flag is set, and incrementing it again, auxiliary carry flag is cleared because there is no carry between the 3rd and the 4th bit. decrementing it. Doesn't change the flag. And now, with the next decrement, the number fits again in 4 bits, so auxiliary carry flag is set again. And the last decrement, there's no borrow from the 4th to the 3rd bit, so auxiliary carry flag is cleared. Do we need this? No. There's not even a jump, call, or reset command in combination with auxiliary carry flag, but the command I will show you does use the status of the auxiliary carry flag and the carry flag to do the correct adjustments. Okay. So the first example, have the number 19 hex, adding 1 to it. These are BCD numbers, I mean decimal numbers, but you have to represent it by the hex value. So, loading the accumulator, adding 1 to it. Result is 1A. Well, that's not a BCD number, so we have to do a correction. And for this, there's one command. DAA stands for decimal adjust accumulator. 19 is loaded, adding 1 to it, and doing the correction. The result is 20. You can also use the add with carry here, or the increment register. But if you use the increment register, don't forget to clear the carry flag before the DAA instruction. Otherwise, DAA will misinterpret the adjustments. Okay. Another example. 93 is loaded into the accumulator, adding 4 to it. Result is 97. Doing an adjustment here, and the adjustment, there's no need to do an adjustment here. So there's no problem. If we are adding, for example, 9 to it, result is 9C. We're doing an adjustment here, and result is 02. And there's a carry flag here, so the result is 102, which is also correct. A problem occurs when you want to do a subtraction. Trend is loaded, subtracting it. Result is 1F. And if the A tries to correct this, here in the simulator it's correct, but on a real 8085 it won't work. I will show it. Let me check this on a real 8085. This one is produced by Siemens. We power up the board. Here we go. Entering the same program. So 3E for loading the accumulator with 20. Subtract 1. DAA and the halt command. Let's do a quick disassemble. Loading accumulator, subtracting 1, and DAA and halt. So I want to put trace on. So here we have our BC registers, DE, HL, stack pointer, program counter, and PSW. The upper bits are the accumulator and the lower bits are the flags. So the first command, loading accumulator. Accumulator is loaded, subtracting 1. It's 1F and DAA, so the result is incorrect. It doesn't work on a real 8085. Let's do the counter check. 3E, it's 19, and the add one is C6, and the rest is the same. Quick check. 19, adding 1, and DAA. So accumulator will be loaded with 19. 19 is loaded, adding 1. Result is 1A, and doing the correction. Result is 20, and auxiliary carry flag is set. Stay tuned for the Z80 part, or otherwise see you in the next video. Bye bye. Before I do the first BCD example, I want to return to the flags. I know I have already covered that in earlier video, but not the H and the N flag. Let's start with the N flag, that's the easiest one to explain. If you do an add or an increment, this flag will be cleared. But if you do a subtract or a decrement, this flag will be set. Which means it's an add or subtract indicator. So for the H flag, which is called half carry flag, it acts similar to the carry flag here, but will consider only the 4 lowest bits. If you do an add or increment instruction, and there is a carry between the 3rd and the 4th bit, this flag will be set. And by a subtract and decrement instruction, and there is a borrow between the 4th and the 3rd bit, this flag will also be set. In other words, if you do an add instruction and the result doesn't fit anymore in 4 bits, the flag will be set. And if you do an subtract or decrement instruction and the result does fit again in 4 bits, this flag will also be set. I will show it in an example, it's easier to understand. Loading the accumulator with E means 14, incrementing it 3 times, decrementing it 3 times, accumulator is loaded, incrementing it by 1. Result is 15. Half carry flag is not set because the number does still fit in 4 bits, and the N flag is 0 because that's an add. Incrementing it again, so result is 16, the number does not fit in 4 bits, so the half carry flag is set. N flag is unchanged, incrementing it again, and here the the half carry flag is cleared because there is no carry between the 3rd and the 4th bit, and F is unchanged, decrementing it. The half carry flag is unchanged, but now the N flag is 1 because there's a subtract command. Decrementing it again, number fits again in 4 bits, so the half carry flag is set, and negative flag stays unchanged. Decrementing it again, half carry flag is cleared because there is no borrow from the 4th and 3rd bit. Do you need to know this? To be honest, actually no. There are even no commands, jump, call or return instructions for the half carry or the N flag. But the command I will show you now is using the status of these three flags, carry flag and half carry flag, to do the correct decimal adjustments. So loading accumulator with 19, adding 1 to it. If you work with BCD numbers, you have to enter them here in hexadecimal form. You can't use decimal notation, but you have to enter them in hex form. And the new command is DAA, that's decimal adjust accumulator. So loading accumulator is 19, adding 1 to it, result is 1A. That's not a BCD number, so we have our correction here, and result is now correct 20. Let's take other values, for example 93, adding 4 to it. (93), adding 4 to it, it's 97. So the result is correct, you don't need an adjustment. What will happen here if you launch the command? Nothing. It recognizes that it doesn't need any adjustments. What will happen if we add, for example, 9 here? (93), adding 9 to it, result is 9C. Doing an adjustment here, so it's 02, but the carry flag is set, which means it doesn't fit in 1 byte, so result is 102. That's correct. Another example. Subtracting 1 from 20. (20) is loaded, subtracting 1, result is 1F. After the correction, the result is correct, 19. The Intel CPU has the same command. Even the mnemonic is the same, but there's a difference. In the 8080 or 8085, there is no AND flag. So the decimal adjustment doesn't know if there was an add or an decrement. That's why after a decrement on the Intel CPUs, the result is not correct. So you can use it only after an add or increment command. Next to the sub command, you can also use sub with carry, or the add with carry, or the increment or decrement. But with the increment or decrement instructions, you have to make sure that the carry flag is not set, otherwise DAA will misinterpret the adjustments. For the Z80, there's even one command left. Actually, 2 commands. So loading HL with a memory address, loading the accumulator with a value 34, and saving that value to the memory specified in HL, loading the accumulator with 1, 2, and now the 2 new commands. Rotate left decimal, we'll do it again, and rotate right decimal, rotate right decimal. HL is specified with the memory address, loading the accumulator and saving it to the memory address. accumulator is loaded now with 1, 2, and the next command is rotate left decimal. So with rotate left decimal, the good news is that the 4 upper bits in the accumulator won't be changed. So we don't care the upper 4 bits. The lowest 4 bits of the accumulator will go to the lowest 4 bits of the memory address. And the previously value of the lowest 4 bits in the memory address will go to the upper 4 bits of the memory address. And the previously upper 4 bits of the memory address will go to the lower 4 bits in the accumulator. So in other words, 2 will go to 4, 4 will go to 3, and 3 will go to 2. 2, 4, 3. Let's do it again. 3 will go to 2, 2 will go to 4, 4 will go to 3. Are you still with me? No? Okay, it's time to go in the other direction. Rotate right decimal. What will happen here? 4 will go to 2, 2 will go to 3, and 3 will go to 4. And the last rotate right, 3 will go to 4, 4 will go to 2, and 2 will go to 3. So we have again 1, 2, and 3, 4. I want to be honest with you. When I started with the Z80 assembler several years ago, I did actually overlook these 2 commands. Well, there are a lot of rotate commands for the Z80, and when I read the first time the instruction of these commands, I thought, what the heck is that? I will do the same example, but with different values. So here I will put 7 in memory, and here I will load the accumulator with 0. Let's do it the smart way. We have already seen this in earlier videos. Okay. 7 is put into memory, and the accumulator is cleared. Watch what will happen here with the first rotate left decimal. 0, 7, and now it's 70. So it's a multiplication by 10, but only because the accumulator is 0. If I do the rotate left decimal again, it's 0, but here we have a 7, which means it's 700. And if you go in the other direction, so 0 again, 70, it's division by 10, rotate right again, so it's 7 again. That's all for the BCD numbers. I hope you enjoyed the video, and thank you for watching, and see you in the next part. Bye bye.